So one very interesting reaction that conjugated dienes can undergo is the Diels-Alder cycloaddition. So I've got two reactants here. I have a conjugated diene. What I'm going to do is I'm going to number the conjugated diene 1, 2, 3, and 4. It's just butadiene, so I'll just do 1, 2, 3, 4, sort of arbitrarily. That reacts with an alkene that has some other functionality attached to it. In this case, it's an aldehyde, but I'm just going to number the two carbons in the alkene 5 and 6. In most cases, it doesn't matter which one we number, but I'm just continuing the numbering from the diene, okay, to the double bonds in this alkene right here. And what's actually going to happen is a new carbon-carbon bond will form between 4 and 5, okay, and between 1 and 6. Just like that. So our product ends up being a 6-membered ring. 1, 2, 3, 4, 5, 6. Okay, that's why it's handy to do that numbering. The new bonds we've formed are the 1,6 bond. There's a new one, and the 4,5 bond. There's a new one right there. So obviously, butadiene, that was the diene. The other compound, the alkene that we reacted with, it's called a dienophile. It's an electron-poor alkene. Why is this dienophile electron-poor? Well, if we look at the aldehyde group that's attached to it, right, C double bond O has a dipole pointed towards the oxygen, so carbon is partial positive. That partial positive sucks electron density out of that CC double bond that's conjugated in with the C double bond O, right? So this is, the dienophile is electron poor. That's a requirement in order for the Diels-Alder reaction to work. The other feature is migration of a double bond. If I were to draw some sort of faux mechanism arrows, we can imagine the pi bond between 1 and 2 making that bond to 6, the pi bond between 5 and 6 making the bond to 4, and then the pi bond between 4 and 3 migrating to between 2 and 3. So I've drawn 3 arrows all around in a circle, and this reaction happens all at once. It's called pericyclic. It happens all in a single step, all at one time. What actually happens is the diene will approach the dienophile, right? Here's the diene, here's the dienophile. The single bonds will start to form just simultaneously while the double bonds are disforming, and our new product has formed. And note the migration of that double bond. We started with 1, 2, 3 double bonds, and we now end with just 1 double bond and 2 new single bonds. Right, we've formed the 2 sigma bonds. We've formed a 6-membered ring. The Diels-Alder reaction is one of the most useful synthetic methods for forming 6-membered rings, especially if they have functionality around them. So we form a 6-membered ring with this nice double bond, which we can use for reactions later on, and so on. This picture right here shows molecular orbitals of the diene and the dienophile. Take a look at the phases of the orbitals that are attaching to each other. Here's the diene, right? Carbons 1 and 4 of the diene have a red-colored lobe pointed towards the red-colored lobe of the dienophile. So there are multiple ways to do this, but it turns out one of them has to be the HOMO, the highest occupied, one of them has to be the lowest unoccupied, because it's actually the highest occupied one that donates electrons into the lowest unoccupied of the other one. And it turns out when you do the relationships like that, it ends up that the orbitals are aligned with each other and are able to overlap. If this were to try to happen with some different combinations of orbitals, if we had a blue one pointing down here, this would not be able to overlap there, and the reaction actually would not occur. So all we need to know is that the orbitals need to be the same phase in order to overlap. right at that point there. A couple important characteristics of this Diels-Alder reaction. I already mentioned that the dienophiles must be electron poor. They will all have some sort of functional group attached to them that withdraws the pi electron density. Okay, that's usually going to be a C double bond to O. That didn't show up. That's a C triple bond N. Okay, those are very common pi withdrawing groups. And ethylene, unreactive, right? 2 electron rich. It doesn't have any group that pulls electron density away from it. I can demonstrate this pulling of electron density away just by drawing one single resonance structure. For instance, for propanal, which has the double bond conjugated with a C double bond O, right? So let's draw one resonance structure. That, because that oxygen is electronegative, it can support those electrons coming up on it. So what I end up with is CH2 plus, then C double bond C, then CO minus. Okay, that's an important resonance structure whenever we have a CC double bond conjugated in with a C double bond O. And in doing so, we have removed pi electrons from that CC double bond over there. We have a resonance structure with those pi electrons outside of it, right? From the molecular orbital standpoint, we would be able to see that these pi electrons are not concentrated within here. They're actually distributed throughout the system. Right there. The C double bond O next to the CC double bond, right, is common in all of these groups. Here we have a C triple bond N. Similar sort of thing happens. I have a resonance structure there where I have an N minus on there. So again, we're pulling electron density out of there. Here I have a CC triple bond, okay, but again, conjugated into a C double bond O that way. I'll show you in a little bit what the triple bond can do in a Diels-Alder reaction. So one important feature of the Diels-Alder reaction is that it is stereospecific, which just means that any stereochemistry within the reactants is retained in the products. It is important to note, though, that all of these are achiral. Okay? There are no chirality centers, so no carbons with 4 groups attached, no tetrahedral. Okay? So we cannot produce an optically active product. If I produce a product with chirality centers, it has to be racemic. So I can write plus minus there next to it, just for us to know that it's racemic, meaning we produce this as well as its mirror image. But let's look at the stereochemistry here. We just have normal butadiene here, so nothing important there. But the dienophile, here I have a Z dienophile. So I've got the methyl group and the C double bond O, both pointed the same direction off of the CC double bond. Compare that with this E dienophile, where I've got a methyl group going one way and the C double bond O coming out the other way. Those two relationships will be transferred directly into the product. So let's do the way we did it before. I'm going to number the diene, 1, 2, 3, and 4. The dienophile, 5 and 6. Okay. We make a new 6-membered ring. Okay. Remember, I form a bond between 1 and 6 and 4 and 5. The double bonds migrate to between 2 and 3. Then the stereochemistry around that ring, since I'm forming 2 chirality centers here, will be the same as the stereochemistry in that dienophile originally. The methyl group and the other groups, right? C double bond O, OCH3, they are cis to each other in the 6-membered ring. You could draw them either down or up, right? Since both enantiomers are formed, but they are cis to each other. Their relative stereochemistry will be cis, because that was determined right here. Let's do that. Okay. If they're opposites of each other, if they're trans-like on that C double bond O in the 6-membered ring product, they will be trans to each other. Okay. And you can draw, I'll just say plus minus to show that the other enantiomer is also formed. So you can just choose to draw one. Okay. So if you draw one up, just draw the other one down. It doesn't matter which enantiomer you draw. But make sure the stereochemistry in your product is consistent with the reactants that you used. If a diene is cyclic, a bridged bicyclic product is formed. These are sort of drawn from the side. I'll draw them from the top just to show you what we're dealing with. I have cyclopentadiene, so a 5-membered ring with 2 conjugated double bonds in it, plus this compound with a 5-membered ring and C double bond O's and an O outside of it. So it has these electron withdrawing groups like it needs. If I number this 1, 2, 3, 4 across the diene, okay, just those 4 diene carbons are what you number, and then 5 and 6, the double bond carbons of the dienophile, we're going to form a 6-membered ring, but this carbon right here that was originally in the diene molecule, since it was a 5-membered ring, this carbon right here will end up sticking up above the new 6-membered ring that we formed. So that's why they have it drawn sort of 3-dimensionally from the side. I'll renumber them here. 1, 2, 3, 4, 5, and 6, forming a 6-membered ring product. Just like that. Double bond has migrated. But then, right here, is this one that is sticking up above the ring. So that's a bridged bicyclic compound like camphor, like when we dealt with it last semester. There are actually 2 options in stereochemistry for where that can be attached. The 2 sort of common names for these isomers are called endo and exo. Okay? Endo occurs when the dienophile comes in underneath, right? Totally all underneath the diene, so that the product ends up pointed down away from the handle of the basket. You can think of that. It's called endo because it's sort of like inside the cavity of this molecule down here. The other option, if we have the diene pointed towards the outside, okay, as this sort of comes upward, the H's on that will be pointed down. So the group we've added is exo because it's outside of the sort of basket, if you imagine holding it like that. Exo is not formed normally in a Diels-Alder product. Okay? It's normally always going to be the endo product. That's just as simple as remembering that the other stuff, right, the C double bond O's and things like that in the diene will end up pointed downwards away from the handle of this basket. Okay? And the whole reason for that is because of extra orbital overlap. Just quickly draw a couple of orbitals right here on 3 and 4. Those will actually overlap with these extra orbitals out here on the C double bond O, okay? Especially carbon 3, like that. Okay? That's different from the actual Diels-Alder reaction where just 4 and 5 are overlapping. So if the diene comes in underneath, okay, its other p orbitals can actually overlap a little bit with the other orbitals further in, and any extra overlap stabilizes things a little bit. Now, that overlap is not retained in the product, it's just within that transition state. But since it lowers the energy of that transition state just a little bit, it makes this endo product form faster. You will probably need to draw a bridged bicyclic compound at some point. Just like that. Keep your lines parallel. It's different from drawing a chair, right? So don't do that. Take one diagonal line and then go both directions up from it, right? And then go both directions down from there. And then you can make the handle to the basket. So you can practice drawing those a little bit. Just like that. So anytime we have a 5-membered ring as the diene, we'll end up with this basket here, where 1, 2, 3, 4, 5 were the original 5 carbons. The 2 new bonds that we formed, I'll draw them in here, right? Just as usual, they're the 4, 5 and the 1, 6 bonds. Okay. There, let's just do that. As the new bonds that have formed. Right, these right in here. And then whatever else was attached to the dienophile will be attached over here. But remember, attach any electron withdrawing groups in the endo position, so going downwards instead of going upwards. The other important consideration to have for a Diels-Alder reaction is that the diene must be able to adopt what's called an S-cis conformation. Dienes are S-cis when their double bonds are pointed the same direction. Okay? Remember, there's free rotation about the single bond in between those. It's restricted a little bit because remember there is some pi electron density between those. So it's not as fast as normal single bond rotation would be, but it still can happen. Okay? So the diene must be able to adopt this S-cis conformation, otherwise that six-membered ring can't form. The S-trans conformation is not reactive towards Diels-Alder, but if this were just your reactant, remember you can have free rotation about that double bond, so it can interconvert S-trans conformation. Where you're stuck is if you have a molecule with, for instance, a ring structure. Say I have two fused six-membered rings and have a diene in there where we have no choice but to be in the S-trans conformation, right? If I go in one ring and then the next ring like that, there's no way this bond can rotate because it's tethered back to the other end. So this compound is not reactive in Diels-Alder. Similarly, this compound, where I have two of really any kind of carbon groups pointing in towards each other, will be too hindered to exist in this S-cis conformation. So watch out for that. This molecule will exist solely in S-trans, which is not reactive to Diels-Alder. Right. So be careful of that. Cyclopentadiene, we show that up above, it's locked into that S-cis conformation and is so reactive as a diene that it will actually react with another molecule of cyclopentadiene, just with one of its double bonds as a dienophile. And it'll form a bridged bicyclic compound called bicyclopentadiene. And that's actually how pentadiene exists. If you had it in a bottle, you'd have an entire bottle of bicyclopentadiene. You can induce the formation of cyclopentadiene by heating it in the other direction, and entropy breaking the molecule in two, will drive it towards undoing the Diels-Alder reaction. But normally, at room temperature, this compound, this bicyclopentadiene, is stable.